Welcome to all. I am Adeline Suji, Associate Professor, Department of Computer Science and Engineering, Kalaignar Karunanidhi Institute of Technology, Coimbatore. Today we can see a topic under spanning tree, and we can see the algorithms which is used to find the minimum spanning tree. First we can see what is spanning tree. Suppose you have a connected and directed graph. Connected in the sense every node is reachable from every other node, and undirected means edges do not have an associated direction. Then a spanning tree of the graph is a connected subgraph in which there are no cycles. Now we can see an example for a graph having spanning tree. You can see a graph having 4 different spanning trees. Next we can see what is minimum spanning tree. A minimum spanning tree is a subgraph of an undirected graph such that the subgraph spans all nodes, is connected, is acyclic, and has minimum total edge weight. Now we can see the 2 algorithms which are used for finding minimum cost spanning tree. First one is a Kruskal algorithm. Another one is a Prim's algorithm. And this Kruskal algorithm, it starts with no edges or nodes in the spanning tree and repeatedly add the cheapest edge that does not create a cycle. And considering the Prim's algorithm, it starts with any one edge in the spanning tree and repeatedly add the cheapest edge and the node it leads to for which the node is not already in the spanning tree. Now we can see the characteristics of an algorithm. Both algorithms, it works with an undirected graph. Both work with weighted and unweighted graph, but if we have weights for edges, then it is more interesting. Both are greedy algorithms that produce optimal solution. Now we can see an example and we can work out both the Prim's and Kruskal algorithm. First we can see the Prim's algorithm. Consider a graph having 8 vertices. Initially, we have an initial array having 3 columns in which column K it represents whether the node is visited or not, and dv it represents the distance of each edge for that particular node, and pv it represents the node from which the distance is calculated, and initially the distance will all have the value infinity and k has the value as false. Now we can start with a node capital D, which is a starting node. So initially we can change the value of k for D as true and the distance as 0. Now we can find all the immediate neighbors of node D. Here the immediate neighbors of node D are C, E, F and G. And we can place the cost of C, E, F and G from D in the place of dv. And we can place the node D in a column of PV for the corresponding nodes. Now we can select a node having the lowest cost which is not visited. And in our example, the node G has the lowest cost which is 2. So we can select G as a second node and we can include G in our spanning tree. So that we can change the K value for G as true also. Now we have to find the nearest or direct immediate neighbors of G. The immediate neighbors of G are H, D and E. Among that, D is already visited, so we can see only H and E. See, for E, the distance from G is 7. But previously, the distance for E has 25, so we can change or replace 25 by 7. And for H, it is already infinity, so we can place the value 3. and we have to change the node as G in both cases. Next we have to choose the next node having the lowest cost, which is C, having the cost as 3, and change its k value as true. Now we find the immediate neighbors of C, which is F, B and D. And here D is already visited, so we have to consider only F and B. For F, already we have a value 18, but here it is, we have from C it is 3, so we can replace 18 by 3. And for B we have previously a value infinity, so we can place the value 4. Now we can once again include the node C in our spanning tree with an edge tree. Again we have to find a node having the lowest cost. In this case we can select F, having the cost 3. Now we have to find the immediate neighbors of F, which is A, B, C, D and E. Among that, C and D are already visited, so we have to find A, B and E. Considering A, previously it is infinity, so we can place the value 10 from F to A. And taking B, previously we have 4, but now we have 7, so we need not to replace, we can leave that. And E, previously it has the value 7, now we have 2, so we can change that to 2. So we can include F into a spanning tree. Next we have to select the next node having the lowest cost, which is E. So now we can change the k value for E as true, and we have to find the minimum or nearest immediate node of E. For E, the nearest or immediate nodes are G, B, D and F. Among that, except B, all the other nodes are visited. So we can see for B, previously B value was 4, but now we have from E to B the cost is 10. So it is greater than 4, we can skip it, so there is no change. Next we have to select next smallest node or node having the smallest cost, which should be H, having the value 3. And we can include H in the spanning tree and find the nearest or the immediate neighbors of H, which is A, B and G. Among that, G is already visited, so we have to consider only A and B. For A, we have previously the value 10, so now we can choose or replace the 10 by 4 because from H to A we have the value 4. And similarly for B, previously we have 4, but now from H to B we have 9, so we can't replace. Next we have to find the next node having the smallest cost, which is A, having the value 4. Now we include A into the spanning tree by placing true in the variable k. And now find the immediate neighbors of A, which is H, B and F. Among that, H and F are already visited, so we can consider only B. And the previous value of B is 4. But now from A to B we have the value 8, which is larger than 4, so we need not change any value for B. And lastly we have a node B, so we are including B into the spanning tree by placing true in the k variable and finding all the nearest or immediate neighbors. All the immediate neighbors have been selected, so here we can stop our execution of algorithm. Finally we will get a spanning tree which is of minimum cost. In our case, in our example, this minimum spanning tree having the cost of 21. Now we can see how the algorithm Kruskal works for an example. This Kruskal, it doesn't consider the edges, or it works with edges rather than nodes. It normally has two steps. First one is it sorts the edges by increasing edge weight, or it's arranged the edges based upon their cost in an ascending order. Next, it selects the first n-1 edges that do not generate a cycle. Here n represents the number of vertices in a graph. Now we can see an example. Consider this graph having 8 vertices and 14 edges. And here I am just arranging all the 14 edges in an ascending order of their cost. Now I am going to select each edge starting from the first one until there is no cycles exist. So here I am selecting the edge DE having the cost 1, and I am including into the spanning tree because it doesn't create any cycle. Next I am selecting DG which has a cost 2, which also included in the spanning tree because it doesn't create any cycle. Next I am taking the third one which is EG, edge EG having the cost 3. But if I include this edge, it will form a cycle in the graph. So I am just neglecting the edge EG. Next I am selecting the edge CD which is included in the minimum spanning tree which creates no cycle. Next I am selecting GH. It is also included in the minimum spanning tree because it's not creates any cycle. And next I am selecting edge CF having the cost 3, which is also included in the graph because it's not creating a cycle. And next I am selecting BC, which is also included in the spanning tree because it not forms any cycle. And next I am selecting BE, the edge BE, if it is included in the spanning tree which forms a cycle. So I am neglecting the edge BE. And next I am selecting BF. If I include BF, it also forms a cycle in a spanning tree. So I am simply neglecting that. Next I am selecting BH and including if it is in the spanning tree which will cause a cycle. So once again I am neglecting BH. And again I am selecting AH. The edge AH can be included in the spanning tree because it will not create any cycle. And since I have reached n-1 edges, in our case it should be 7, I can neglect remaining edges. So finally I will get a minimum spanning tree with the lowest cost having the cost value 21. Thank you.